I asked ChatGPT, can you please make a list of the main bibliographical references on numerical methods for the control of wave-like equations? And then I got some references, including a book by Blovinsky and Lyons and so on. And then in number 5, I get this reference. So it's propagation, observation, and control of waves, blah, blah, blah. And then it says in Handbook of Numerical Analysis with pages and so on. So it looks very convincing, right? So the author, the title, the year, the publisher, the book, the pages. Okay, well, on the pages you see, well, the paper seems to be 312 pages long. It's a bit a long paper, but maybe you don't pay attention to this. So it's very believable that, that this paper exists. Actually, it doesn't exist. So I can recognize my name, the year, and the title. And this corresponds to the paper I have shown you below. This is a Science Review paper published in the year 2005. But so the author, the year, and the title is correct, but the publisher and all the rest is fake. So the publisher is known for us. I think actually even together with Enrique Fernández-Cara, we were contributors to one of these handbook books on the state of the art in numerics for control problems. But you know, ChatGPT is mixing things. Now it's taking the title and the author of one paper and mixing it with the publisher, the volume of another paper. So you have to be careful. So you see that this generative capacity of ChatGPT is compatible with generating virtual things that don't actually exist. As we said yesterday, when you are asking to ChatGPT to draw a portrait or a picture of a given scene you have in mind, you know, I don't know, you biking on the mountains in, you know, in Andalusia, you know, seeing in the horizon the Mediterranean and so on. Then if it makes it very creative and very artistic, you say, oh, ChatGPT is great. But when you are trying to build a bibliography, you don't really want that ChatGPT becomes creative, but rather that remains precise, right? Adapted to the real truth. So there are therefore two aspects that you have to take into account, is that ChatGPT and every machine learning model is based on nonlinear approximation theory. So you are not only simply gathering information that you are reproducing. This is what Wikipedia does. So everything that is written in Wikipedia, there is a writer, there is a moderator, it can be edited, it can be checked, it can be erased, it can be improved, it can be corrected. This is not what ChatGPT or machine learning does. Machine learning takes partial information and builds a nonlinear function that is aimed to reproduce a much complex reality, because the partial information you have is just partial. In some cases, when you are dealing with very carefully treated applications, maybe there has been a priori some statistical work that has been done so to guarantee that the partial samples, the information you have gathered to later train your model, so the data set you have built is reproducing in a statistically correct manner the function you are trying to, the complex, say, model or function you are trying to approximate. But this is not what we do typically. We just gather data, and with the data gathered, we try to build, say, naively, in the sense that we just adopt an architecture, an activation function, and we optimize parameters with the given information, and without any kind of a statistical guarantee. We are just hoping that the function we will build using neural networks will be able to capture well the existing reality, and you see what happens. So this is not MathCNet. This is not an encyclopedia. This is not the Wikipedia. This is not Google Scholar. This is ChatGPT. So ChatGPT is taking partial information and is trying to offer you a product, and then the product is X% accurate. Maybe it's 90-something% accurate, which is amazingly successful, right? But it's not 100% accurate. And this is what you need for a bibliography. If you submit a paper with such a bibliographical reference, you know, and you get to the referee that knows the topic well, probably the referee will say, well, I mean, you better don't publish this paper that probably has been built using ChatGPT. So, you know, if there are errors in the bibliography, why no errors in, you know, in the proofs or in the statements of the theorems? And this somehow is also related to one of the questions that arose yesterday about the use of this kind of tools for solving mathematical problems. So there are experiments, there are projects ongoing using ChatGPT and in general machine learning tools, large language models and other machine learning tools to solve, for instance, the problems in the mathematical Olympiads. And well, there is a high level of success, but, you know, you have to double check. This is like a professor correcting exams of students that are all very, very good. Well, so you know that the level of success will be very high, that the marks you will put will be very high, but probably there will also be errors in the arguments and some gaps. And this is what still happens whenever you use these kind of tools, because they are not built in order to systematically guarantee correctness, right? They are not exhaustive. They are just interpolating and therefore guessing. So we have to keep in mind that ChatGPT is pre-trained, is generative. This is good, but be careful, right? So there are some applications in which you don't ChatGPT to be, you don't want it to be generative, you want it to be accurate. And for that, there are other computer science tools based very much on logics. There are projects ongoing in which you can rewrite a whole article or a whole proof in a language that the computer can understand and can follow every single implication in your argument, and eventually, in case there are, be able to detect, right, any gap in the proof. But this is a different project. This is very much computer science plus logic, much more than simply interpolation through neural network. So if you want really to have guarantees that the computer is assisting you on the checking of a proof, you really need to write this down in a way the computer will understand, and then the computer will check. For instance, that when you say, you know, theorem and then proof, you say, I'm using the induction principle, and therefore, let me check that, assuming that the statement has been proved for the first n items, I'm now checking it for the next one, n+1. And then you do a very complete proof of this. The computer checks, the computer agrees, but then the computer tells you, oh, but the proof is not complete because you didn't check that you can show the property for the very first item. So the induction principle is not complete. You check that n implies n+1, but you forgot to check it for the first instance, okay? So this is something else. It's a different kind of use of computer science and logics for, say, the verification of mathematical proofs. But certainly all these new technologies are incoming, and there will be more and more present in the mathematical sciences. So to insist a little bit on this aspect of, say, not having complete guarantees of what we are doing, I think it's good to revisit very briefly what I said yesterday about what is the foundation of everything we are doing. So the origins go back to at least this Tauberian theorem by Norbert Wiener in 1932, and the later development, Sivenko, and many, a very, very broad literature on approximation theory. Enrique was asking me about, for instance, are there extensions for functions defined in infinite dimensional spaces, Sobolev spaces, thinking, for instance, on evolution PDEs in which you are considering spaces of the type LP, with respect to time in 0, capital T on a time interval with values in a Banach space or in a Hilbert space, something that is so typical in the functional analysis of evolution equations. And yes, there is a very broad literature on this. And I'm not an expert on this. So I know, for instance, there are also very careful analysis of how well these nonlinear approximation methods perform compared to others, like, for instance, finite elements. There is, for instance, a survey article by Ron DeVore and collaborators in Acta Numerica, published probably 2021 or 2022. You can find it easily in Google. But so going back to this very statement of Sivenko, as I said yesterday, the proof is based on Banach. So maybe I can take just a couple of minutes to show you what is the idea. So this is what we said. We take, for instance, this activation function, the sigmoid activation function, sigmoid, taking asymptotic values here equal to 1 and here equal to 0. And here equal to 0. I consider this ansatz, the sum from 1 to n of wk sigma of ak dot x plus bk. And I want to show that this can approximate a function f of x. So the function f is defined from Rd into R. Okay, so then the notation, recall that sigma is a function of one single variable. So this has to be an scalar. Therefore, this drift term is on the real line. This dot stands for the scalar product. X is the variable, of course, in Rd, and therefore AK is a direction in the space Rd. And then W is just the scalar weight you give to each of these neurons, right? So this is a very simple neural network. Neural network is simply the linear combination of neurons in this case. The neurons are each of the items in this sum, okay? So each of these is one of the neurons. And in this case, as I said yesterday, this is the particular case where the neuron is, the neural network has only one layer, right? And it's very wide. The width is very large, it's very tall, right? But it's very, very, very shallow. There is no depth at all, just one. In this particular case, as I said, we claim density, and the proof that Sivenko does is the following. I just give you the idea in 1D so that you understand what's going on. So the proof by Sivenko uses Banach and therefore argues by contradiction. It says, assume, this constitutes a manifold. So this set of all functions of this form constitutes a manifold. A manifold n, once you fix the n, in which, what is the dimension? As we said yesterday, the dimension is going to be n times, and then here you have 1 plus d plus 1. So you have that the dimension of this manifold is n times d plus 2, okay? So it's a large dimensional manifold, but it's not a subspace. It's not a subspace. Why? Because as we said, sigma being nonlinear, the activation function being nonlinear, this ansatz doesn't depend linearly on the parameters AK and BK. So you have nonlinear, like distorted high dimensional of dimension n plus n times d plus 2, nonlinear distorted hypercube in the Euclidean space you are living on. So assume, for instance, we are in L2 of RD. So in this Hilbert space, you have this nonlinear manifold of this dimension embedded in this space. So we are not doing classical Galerkin approximations or classical linear approximation theory in which you expect that the function in the high dimensional or infinite dimensional space, in this case, L2RD is an infinite dimensional Hilbert space, is approximated by looking for the elements that are the projections into subspaces that are increasing in dimension. And this is what finite elements, Fourier, or polynomial approximation does. This is different. So these manifolds are nonlinear. Okay? Very good. But still, we can keep our intuition saying, well, maybe the manifold is nonlinear, but maybe I can think that this is like an elastic hypercube of this dimension that is a little bit distorted. And of course, when the dimension increases, this the form of hypercubes anyhow will end up filling the whole space and will guarantee that I can approximate every f, right, with such an answer. Of course, the goal, of course, is to show that if you take, for instance, a compact set, we just do it locally, right? We take a compact set, then we give an epsilon. There exists an n, a natural n, a sufficiently large number of terms in this series, and then the corresponding coefficients for k from 1 to capital N, such that the gap between the function f and this ansatz here, that I will not rewrite, in L2 of the compact set is less than epsilon. Okay, this is the goal. So argument by Sivenko. Let's do it by Hambanach. Hambanach says, if this density property is not true or not true, there will be a function h, there will be, no, if not, there will be a function h, non-trivial, and h will be orthogonal to each of these possible sums. Oh, but if h is orthogonal to all these sums, then in particular, h will be orthogonal to every single neuron, right? So the function h will be orthogonal to every single neuron. So this means that the integral of h times sigma a dot x plus b dx will be equal to 0 for all choices of a and b. So now what is sigma ax plus b? As I said yesterday, the only thing we are doing with the coefficient a and the coefficient b, we are moving the center of gravity of the sigmoid sigma from 0 to the point minus b over a. And then with the a, I am just regulating the slope of the sigma. In particular, by letting a go to infinity, I can guarantee that this slope becomes steeper and steeper, and eventually the limit of sigma is going to be the Heaviside function. So you see that because this orthogonality property is true, then h is going to be, in particular, orthogonal to any Heaviside function. Of course, by taking a to be of the opposite sign, to be negative, you can also orient the Heaviside in this manner. So the conclusion is, if h were orthogonal to every function of this form, then you will have that the function h will have a 0 mean on every interval from minus infinity to any point L, but also the integral from L to plus infinity of h will also be 0. So you will have a function h because of this orthogonality property that has 0 average to the left and to the right of any point, in any half line, either oriented to the left or either oriented to the right. And then the question is, what is the unique function h which such a property for all L? And then, of course, the only function is the 0, 1. Why is this? Well, because if I want to show that h at this point is equal to 0, it is sufficient that I compute, averages on small intervals of size delta around that point. If h is continuous, then, this is a trivial limit. If h is L1 or L2, you need to use Lebesgue differentiation lemma. But it's true, in any case, that h almost everywhere is the limit of averages on small balls of radius delta, as delta goes to 0. And what is the integral in this little ball? Well, the integral in this little ball is the integral over this half line minus the integral over this half line. But because of the two integrals in the two half lines are 0, the difference is 0, the integral on this interval around that point x is 0, and then by the limit, you get that h is equal to 0. That's the idea of Hambanach. Okay? So this is one possible proof. The other one, if you are an expert or you know a little bit at least of finite elements, you recall how finite elements work. So the comparison with finite element theory. So how does finite element theory work? It says, okay, take the real line. You can extend it to multi-D, of course, but take the real line and take a mesh. You don't need the mesh to be uniform, but typically, at least in the preliminary statements, the first results for finite elements, you will consider a mesh which is more or less of size delta x. What does it mean, the mesh to be of size delta x? Well, it means that all the lengths of all these intervals in which I am splitting the real line, all these intervals will be in between, say, alpha and beta times dx, okay? So you don't want too much eccentricity on your mesh. You can think of, as an example, on the classical regular mesh in which you have a mesh size h and you keep it for all intervals. Okay, so in these conditions, we know that the finite element theory guarantees nice convergence properties for the Laplacian or for other PDEs. But in fact, what is true, and this is what makes finite element theory powerful, is that it tells you, listen, actually, if you give me any function f, and then you approximate it on this mesh, say, in the Sobolev space H1, right? You get something like this under the condition that f is in H2, right? This is the classical approximation theorem for finite elements. So now, once you know this, then you can immediately understand why Sibenko works. Because if you think, for instance, in the case of the ReLU, when the activation function is the ReLU, and then you think on what this is, at least in 1D, you see that each of these neurons, each of these terms that we are introducing in the sum is a ReLU function. You are translating, regulating the slope of the different ReLU functions. You are superposing them. So what do you expect in the end to be the shape of this function? Well, you expect indeed to have also a finite element function as the one you get here, right? This is the finite element approximation, as you know, eventually, just to give one value in every node and then simply interpolate piecewise linearly, we get the same kind of functions. So then, at least in 1D, Sibenko is true, of course, because we know already that the finite element method has a good approximation property. What is, in your opinion, the main difference between Sibenko and the finite elements? So the main difference between Sibenko and finite elements is that in finite elements, I fix the mesh a priori, while in Sibenko, I have complete freedom on choosing A and B. And when choosing A and B, as I have shown you here, you are choosing the switching point where the ReLU, right, is localizing its 0. was written here somewhere, okay? So this point here will be minus B over A. So what you have with the ansatz a la Sibenko is not only you can build every function that you can consider within a mesh of a finite element approximation, but actually you have the union of all the finite element functions you can consider, you can build in all possible meshes. So then if you ask me, is Sibenko's ansatz guaranteeing density? I tell you, well, not only density, you have super density, you have ultra density, because just choosing one single mesh in finite elements guarantees already the approximation property you are aiming. And here you are taking the union of all the finite element meshes and all the possible finite element functions that you can build in all these finite element meshes. Then, of course, you have density. So is it better to have density or super density? In principle, one would think, well, it's even better when you have super density because you have so many possible choices. Well, it's not true. When we are, doing approximation theory, when we are in the context of computational mathematics, it's much better when you have only one single approximating ansatz, because then you are looking for that one. While here, you have so many possibilities. There are so many combinations of A, B, and W for the different neurons that guarantee density that you face the embarrass of choice. And this is precisely what happens when you think naively on a least square approximation methodology. You will say, well, if I want given n, so given n, large, if you ask me, can you compute the coefficients W, A, and B for approximating the function f, then I will minimize on the space of AK, BK, and WK, which belong to RD plus 1 from K from 1 to N. I'm sorry, I have to minimize the norm of N minus this sum in L2 to compute the optimal coefficients. But as I have said yesterday, despite of this superdensity property, or precisely because of this superdensity, not only the density, this ansatz depends non-linearly on the coefficients A and B, and therefore this functional is non-convex and is not easy to find its minimizers. Actually, you can never guarantee that you got to the minimizer. You will apply a stochastic gradient descent, you will have high probability of being close to the minimizer, but you don't have the minimizer. Not only this, once you have solved this problem for n, if you realize that the gap you get for capital N is too small, and you want to increase the n to say, okay, let me consider 2n, for instance. I double the number of neurons in order to get a better approximation. The values you have computed for the first n terms are not the ones that will guarantee optimality for the 2n ansatz. So you will have to recompute all the coefficients again. So you see that you increase significantly the computational complexity. And then what happens then when you ask for the bibliography on a given topic to ChatGPT? Well, ChatGPT, as I said before, is taking items, right, that are, true, and then using this finite element Sibenko kind of free nonlinear ansatz in which meshes are variable and coefficients and weight can be chosen, is making some kind of interpolation, nonlinear interpolation, okay? So you say, well, this is a very good idea, yes. But then when you ask for the bibliography on a given topic, what maybe ChatGPT is giving you this. And this is what? This is a virtual paper, never written, never published, in which you are taking elements of this one, maybe author and title, but maybe you are taking elements from this one, like publisher and year, for instance. And this is why you see virtual things happening. So I insist, all this is very much related to the nonlinear character, and the goal of machine learning itself is not to, in principle, is not to provide 100% guaranteed answers, but rather to quickly deal with complex tasks with a very high probability of success. Okay, good. So this is the point we were yesterday when I wanted to show you this video of 3 blue, 1 brown, just so that you get a little bit the aroma of how the classical tools we know in numerical analysis, in discrete mathematics, in control theory, in dynamical systems, in probabilities, how these ingredients are combined in a very original manner to tackle these problems. So I will try to open the first video. Let's devote a few minutes to enjoy it.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic. And I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years, there's been sort of a boom in research towards these variants. But in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons. And admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network as an information processing mechanism comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits. And let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge. Or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with the 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own. And I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number. But for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases, 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra. So for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing. Now is the point I suppose I should say subscribe to stay notified about when that video or any new videos come out. But realistically, most of you don't actually receive notifications from YouTube, do you? Maybe more honestly, I should say subscribe so that the neural networks that underlie YouTube's recommendation algorithm are primed to believe that you want to see content from this channel get recommended to you. Anyway, stay posted for more. Thank you very much to everyone supporting these videos on Patreon. I've been a little slow to progress in the probability series this summer, but I'm jumping back into it after this project. So patrons, you can look out for updates there. To close things off here, I have with me Leisha Lee, who did her PhD work on the theoretical side of deep learning, and who currently works at a venture capital firm called Amplify Partners, who kindly provided some of the funding for this video. So Leisha, one thing I think we should quickly bring up is this sigmoid function. As I understand it, early networks use this to squish the relevant weighted sum into that interval between 0 and 1, kind of motivated by this biological analogy of neurons either being inactive or active.
Exactly.
But relatively few modern networks actually use sigmoid anymore.
Yeah.
It's kind of old school, right?
Yeah, or rather, ReLU seems to be much easier to train.
And ReLU stands for rectified linear unit.
Yes, it's this kind of function where you're just taking a max of 0 and A, where A is given by what you were explaining in the video. And what this was sort of motivated from, I think, was partially by a biological analogy with how neurons would either be activated or not. And so if it passes a certain threshold, it would be the identity function. But if it did not, then it would just not be activated, so be 0. So it's kind of a simplification. Using sigmoids didn't help training, or it was very difficult to train at some point, and people just tried ReLU, and it happened to work very well for these incredibly deep neural networks.
All right, thank you, Leisha.
Okay, So what do you think? Comments, questions? So you see that there are plenty of ideas involved. Actually, I recommend you to watch this video slowly yourself to better capture the ensemble of the details. There are many. Let me go back to the beginning.
But if I told you, hey, sit down and write for me.
So you see, to begin with, what kind of application we have in mind. So we want that to build a machine that is able to recognize digits out of human drawings. This is something that we as humans can do very easily, even when we are kids. I don't remember when kids learn to identify the 10 digits from 0 to 9, but this comes very early, okay? So now we want to build a machine that will be able to do the same task. So this is very much also related to the question yesterday about, whether we expect machine learning or artificial intelligence to replace humans in reasoning. And you see how complicated it is to build a machine that will be able to replicate this very simple function that a human brain learns very early, recognize digits from 0 to 9. Okay, that's the first thing. So we are very far, and it needs a lot of mathematics, very clever mathematics, not very deep, maybe. We are just employing very elementary ingredients all the time, but the cooking is very sophisticated, and it got quite far, right? This is like, there are very good cookers, there are bad cookers, there are medium cookers. Basically, they all use the same kitchen, the same oil, the same tools, the same ingredients, but the output sometimes is fantastic and some other times is just very poor. So here is the same. So it's just the way we combine all ingredients that makes the success of the ensemble. It's not really that we are using very, very deep mathematical ideas in any of the steps, okay? Well, now this is the first thing, what we are doing, how we are going to do it. The second comment I wanted to make is what you cannot expect, because if you, for instance, so if I write a date, say, so we all recognize here, right, the date. Now, if I just write a number like this, what is this number in your opinion? What is this digit? Well, if I write this, there is no doubt. This is a 4. If I write this, this is a 6. If I write this, well, maybe it's not that clear. Well, Europeans, we used to write 7 like this, but I think it's in North America, they don't use this very often, this horizontal trade. So you see something like that, you will say, well, it can be a 1 and it can be a 7. So you cannot really guarantee what the output is. You can simply allocate high probabilities. And this is what the neural network is doing. Okay, so we don't expect the machine to be 100% accurate. The machine will simply learn to allocate probabilities to the different drawings you do. Okay, so this with high probabilities are 3, but you could think that, well, if these the extremes of these 3 were closer together, there will be some probability that this is also maybe an 8. Okay, so then the output, this is like a Markov chain. So layer by layer, the information is evolving. And eventually in the last layer, what you expect, and this is drawn in the video, explained in the video, what you expect is that you get an exit, a vector, a probability, discrete probability vector that is all allocating a weight to each of the 10 possible digits from 0 to 9. So a positive weight for each of them. The allusion is going to be 1. And then what you expect is not that you get certainty, complete certainty, like a Dirac delta telling you, the computer will not tell you this is a 3, 100%, will not give you probability 0 for the 0, 0 for the 1, 0 for the 2, 1 for the 3, and then 0, 0, 0, 0 up to the 9th. So the computer will give you something which is close to a Dirac delta, but there will be noise. There will be also some small contributions in the other because we are not really, the code, the algorithm is not built in the way that it is guaranteed that you get a Dirac delta. If you want a Dirac delta, of course, you could do some a posteriori processing. And you could say, well, listen, out of any vector, discrete vector, I can always try to determine what the Dirac delta should be. And there are very clear cases. If you give me, probabilities below 0.1 in every entry, and then at the 3, you get 0.97, well, it's very easy to say, well, this is the Dirac delta. This should be approximated by the Dirac delta at 3. So with very high probability, I can say this is a 3, or I can even guarantee that this is a 3 with some very mild room for error. But when you are in different situations, like this case in which we were recitating whether I draw a 1 or a 7, if you see probabilities very low for most of the indexes, for most of the entries, but at 1 you see 0.41, and at 7 you see 0.43, and then if I ask you, please, you have to approximate this by a Dirac delta, well, you will tell me that then this is a lottery, because the realistic approximation should be half Dirac delta at 1 plus half Dirac delta at 7. But it will be a 2-atomic measure. It will not be a monoatomic measure. Okay, so this is the second aspect in this. Okay, then there are many other aspects in the video. Well, another aspect is, for instance, this is the fact that you don't try to do it in one shot. You don't try to do it in one shot as Sibenko's ansatz, in which there is only one layer, but you try to do it gradually. Okay? So the next ingredient you see clearly represented here is that the number of neurons starts increasing rapidly, and the number of coefficients increases even further. So the dimension of the problem, of the training problem, which is a non-convex optimization problem you have to solve to compute the optimal or nearly optimal values of the parameters, needs to be large. Okay? The other aspect is that this is a supervised learning exercise. So in order to build this network that will learn how to identify digits, you need to give to this network a data set of many ones, many zeros, many digits written in different forms by different individuals with different computers, with different type of, for instance, we write in Word, and then we can change the font. And in some fonts it's easier to read, in some others they are more artistic, more calligraphic, maybe it's harder to read, but we can all read, identify text in different fonts. Well, we have also to show this to the computer. We will have to show different writings of the same digits in different fonts so that the computer understands that all those digits written differently, either by hand or in a printed manner through computers or machines, they all belong to the same class of the two, right? So this is a monumental task. So This is a supervised learning exercise in which we will give to the computer many digits written and printed in different ways with the corresponding label. And we will show to the computer 2, this digit there, this is a 2. So this means we teach to the computer the exit for this picture. See, this is just a picture, right? An image is 001 00000. So we feed the computer with deterministic and correct labels. Of course, if we make mistakes, something that happens because there is human intervention, and someone, when putting the labels on the program in which we are building the data set that the neural network has to absorb to learn, if there is one error and someone says, oh, I thought this was a 4, I was not paying much attention, or I didn't have the glasses on, so I wrote this is a 4, then you are contaminating the data set. And if you do that, please don't expect that the neural network will correct you. The neural network will try to absorb all the data. Okay? Of course, because you are, if you are using, I don't know, 100 2s, and you only do a mistake on one of the labels of one of the 2s, maybe this will affect the whole training process in a very mild manner. But it will definitely affect, because whenever you change the data set, whenever you change the labels, you recall, this was shown in the slides, we are modifying the loss or the cost functional we are minimizing, and therefore we are also changing the values of the actual minimizers. Okay? So now, of course, we need also to answer to the very first question of how do I move from the context of images to an Euclidean context where I can use neural networks analysis very much like in Sivenko ansatz and our early discussion about density. Well, it's very simple. You take photos. Every photo is a number of pixels. So every drawing you do of any number will become just a vector in which you allocate one value of each to each pixel. So you see here already that not only we have many neurons and many parameters and high dimensionality because of the number of parameters you have to optimize, but necessarily you will be working in high dimensional Euclidean spaces. So a very rough picture, very low resolution picture with 28 times 28 nodes, this brings you to Euclidean space dimension 784. So you see that in the context of machine learning, high dimensionality appears. There are, we are like in a living room and all doors lead to high dimensionality. The space dimension, the number of neurons, the number of parameters, everything is high, okay? So then there is this idea of iterating. There is this idea of iteration, layer by layer, because we have to learn the neural network learn. And for this, the same way humans, we need to read a text and then read it again, and then read it again, and then underline in order to really integrate the main content and have clear ideas of what are the key words, the key concepts, the key proofs, and then somehow internalize the ensemble of a given theory. The neural network needs to iterate in order to do this, okay? So we are mimicking layer by layer the human process of learning by repetition. And then you see that there is this idea of decomposition. So because we have to teach the computer what is a 9, for instance. Well, basically a 9 is
similarly a long line, like the kind you might see in the digits 1. Or...
A 9 is like a 0 plus a 1. Okay, so it's just the superposition graphically of a 0 and a 1. and we have to teach this to the computer. So it's very hard to teach that to the computer if we are just using, complete digits. We have to decompose it into pieces. So this is the very very classical principle of divide to conquer, the one that already is traditional in applied mathematics. You all can imagine things like multi-resolution wavelets, domain decomposition, operator splitting are very much based on these ideas. And this in particular can be done thanks to the use, and this is where the nonlinearity of the activation function enters. So the sigma helps you on doing this, because the sigma allows to prioritize preserve some of the values while killing the others. So you see, for instance, that there was a representation of the 9 here. Maybe it was here. Okay. So here is the 9. So roughly, how do I represent a 9 through a vector? Well, basically, I will say that in all these, so I need a matrix 28 to 28. I can even put it in a vector. I just order these entries on the matrix on a 784 dimensional vector. So I will allocate a 0 to all these nodes, all these coordinates, all these components where there is no trace of the digit, and whenever there is, I will allocate a 1. Then in practice, of course, there are also shadows, there are grays. You could think on something that is not purely bang bang 0 1, but basically this is what it is. It's just a vector with many zeros, most of them zeros, and just the ones collocated on the coordinates that allow you to draw the 9. You see also here some levels of gray, like 0.7 or 0.2, but we can think just on zeros and ones. But we have said that a 9, we as humans, we see it as a superposition of a circle and a vertical line, basically. So I can just separate the circle from the vertical line by passing a sigmoid function across this interface. Because you see, in the multidimensional case, in the sigmoid, we are dealing with vectors, and therefore these vectors allow for orientation. This is something that is also represented here. It was somewhere here, maybe here. Okay, so you see the weights we are employing here to do scalar products allow us to not only focus on a specific horizontal or vertical regions, but even make oblique choices. So the sigmoid allows to zoom, the sigmoid allows to split, the sigmoid allows to build small elements out of the big ones. But because we are repeating along the neural network, we can also glue the different components in order to finally come with a good guess of what every drawing of any possible digit could be. Well, so I definitely think as professors, we have to take into account that these tools are on students' hands. So then we have to work harder to think on what exercises we can ask them to perform. How do they have to study? So to guarantee that they are really getting into, learning and not simply replicating. This is definitely a challenge that will modify the way we teach. So certainly we have to ask questions. If, I ask a student, say today is Tuesday, okay, I'm asking students, please deliver a work of 5 pages on a given topic for Monday. Well, so I know that most of this work can be done automatically by ChatGPT. Indeed, if I am asking, can you please tell me something about, I don't know, Lyapunov functions? So we can try. We can also try this. So I'm just guessing. So if I Google, I go to ChatGPT again. And then I ask ChatGPT, please tell me about Can you explain me? You see my screen, right?
Yes.
About Lyapunov functions. The main mathematical ideas behind its uses and historical background. I insist that this is the free version of ChatGPT. I don't have the professional one. And then you see the text. You see it here, right? So immediately, instantaneously, I got here definition, Lyapunov function, the dynamical system, what is requested, Lyapunov stability, asymptotic stability, the mathematical intuition, the notion of equilibrium, this analogy with, gravity forces attracting balls, uses of Lyapunov function in control, in economics, in biology, in chaos theory, historical background. So we see here data about Lyapunov, who wrote his PhD in the late 92. Okay, so Lagrange, Jacobi, key concepts, global stability, conclusion. So, it's extraordinary, right? So we as professors, we have to think what we are asking to the student. So, and we have to do it very carefully because soon ChatGPT, I don't know, maybe ChatGPT is already able to do that. I didn't try. Certainly ChatGPT can do much more than ChatGPT 3. I don't know whether anyone here knows whether if I ask ChatGPT, I write a dynamical system in finite dimension, nonlinear dynamical system in 3D, for instance, and I ask ChatGPT, please give me a Lyapunov function, will ChatGPT give me this? Probably yes. So maybe not with 100% guaranteed, but once you get the Lyapunov function, you can check yourself that this is really a Lyapunov function by computing derivatives. So definitely this is changing the landscape of mathematics and also mathematics education. Yeah. So there are other questions here. Are there something in math about the functions used in approximation like the one of Sivenko or other winner? I thought same function that Nico is used, which is also used for rebuilding a function from its samples. Well, so there are many functions. The sinc function, I think is the Fourier transform of the characteristic function. So the characteristic function is kind of a limit of a Gaussian. It's also a way of focusing on specific parts of a Euclidean space, either in space or in Fourier. So all this is related, of course. But as you have seen in this video, well, people in machine learning try to make things as simple as possible and make it practical. I have a question. The different layers are matrix of other samples, like same number written by other people. Well, maybe you are right, Juan, but I don't see it that way. I see more like, this is a dynamical system in which information is evolving layer by layer. And then you feed all the data you have on your data set as initial data. You tell the dynamical system what the output will be. This is the label, features and labels, features in the entry and labels in the end. And then the dynamical system has to adapt itself so to be able to allocate for every initial datum the corresponding output. Okay. So I don't see that. So I see more like I've said that the number of the dimensions in the space of images of digits was 784. What I see rather is that layer by layer, we are making this digit evolve in the space of images, maybe also splitting, losing components, gathering components, and so on. We are making this digit evolve so to eventually land in the corresponding configuration, which is probability for the digit 0 to 9. So you see also that the input space and the output space is not the same. The input space is of dimension 784 because I need 784 components, pixels, to guarantee a good resolution of the image. So the input is an Euclidean space of dimension 784. The output is the space of dimension 10, where I expect a probability vector just telling me the probability of each of the digits to be the ones represent the new image, okay? So for those that are familiar with PDEs and evolution PDEs, I think there are a few here. So let's see what is the most prototypical PDE. There are basically three: Laplacian, waves, and heat. Let me consider the heat equation, which is probably the one that is closest to what we are doing here. So what does the heat equation say? So you open the book of Friedrich-John or the book of Evans, so they will tell you, listen, this is actually something that Gauss did. Gauss was the one who introduced least squares. Least square is the best possible linear approximation of a cloud of points. We could say that Gauss invented machine learning by introducing this very principle of least squares, which is fundamental in data science. So you have data. The data are a cloud. A cloud is complicated. I mean, a cloud is a cloud. It has a shape, has different densities in different regions. You cannot expect to represent a cloud by something very elementary, but still you can try to find the line, the real line that better fits the cloud. And this is, least squares. This was Gauss. This is maybe the starting point of machine learning. In machine learning, then what you do is you make this line to evolve into a much more complicated pattern, not only a polynomial. It will be very natural to say, oh, you try with a line, now you try with a parabola, you try with a polynomial. Why not with a neural network, a Rasidenko? Why not through a neural network construction with different layers and different widths? And this is how machine learning arises. But probably we could claim that Gauss invented this. Gauss also solved the heat equation in 1D, and he said, listen, if you solve the heat equation with a given initial datum, the solution U at point X at time T is given by the convolution of the initial datum with the Gaussian evaluated at point X, where the Gaussian is 4 pi t minus 1 over 2 exponential minus x squared over 4t. Okay, I think this is the explicit expression. You can find it. This is the Gaussian, the fundamental solution of a heat equation. Okay? So people used to say this is the fundamental solution of the heat equation. Well, Tikhonov said, listen, there are others, so you should not say the fundamental solution of the heat equation, but basically it is, because this is the only fundamental solution of the heat equation, which is, for instance, bounded in space for any time. This is the only fundamental solution that is non-negative. This is wider theorem. So basically we can take into account that there are some pathological examples. If we exclude them, we can say that this is the unique fundamental solution of the heat equation, so that it fulfills indeed the heat equation, as you can check easily by algebraic computation, and it takes the value at t equals 0 is the Dirac delta at x equals 0. And then I'm using just the properties of derivatives with respect to the convolution to guarantee that, well, because this is the fundamental solution, I can get any other solution by just making convolutions with the Gaussian. Okay, very good. Now, what does the Gaussian do? So the Gaussian is like, it's a mixer, right? And the more time you let it evolve, the more it mixes. So the Gaussian starts from a Dirac delta at t equals 0, increases its variance, right? So, and then at t equal 1, at t equal 2, and when you go to t equal infinity, you see something that is very flat. But you see, we see the Gaussian as a decaying function, and actually decays, because you see that the maximal amplitude here of this exponential is going to be 1. The 1 is located at x equals 0, where the argument here vanishes, so exponential 0 is 1. And then the decay in time is like t minus 1/2. So the Gaussian actually decays. But by decaying, the mass inside is always preserved. Right? How is the mass preserved while the L infinity node decays? Is because basically the support is spreading. And this is what you see here. The mass is conserved because this is actually a function of a square x, a square root of t, right? Something like this. Okay, and you see this square root of t here, which compensates the Jacobian of the change of variables. So the mass is conserved. So the heat equation, the only thing it does is like a very democratic system in which you take the wealth that is concentrated just on one single point. All the wealth is accumulated at x equals 0, and then you diffuse it to all the population in this Gaussian manner. Of course, those that are close to 0 always are wealthier than those that are here that only get an exponential q, but you are, at a rate of the order of x over a square root of t. So parabolically, this is why it's called parabolic, because there are parabolas involved. So if you will make this to be constant, then this will mean x over square root of t, or in the other, right, s squared equals ct. You see parabolas. This is the wealth is distributed. Diffusion acts on a parabolic manner. This is why it's a model that is universal for heat diffusion, but also in population dynamics, the spreading of populations, the infectious diseases, many other social phenomena like panic on stock markets and so on. Things diffuse very, very rapidly. Okay, very good. Now, what does the Gaussian do, in your opinion? If I will take an initial datum like this, let me give you an example. I take an initial datum like this, U0x. I take this initial datum, right? And then I ask you, could you please tell me what's going to be the solution of the heat equation, which is just the convolution of the Gaussian with u, so uxt. What's going to be like when t is very, very, very large? What is, in your opinion, the solution will look like? You can write it in the chat, or you say. Flat. Flat means what? Constant? Constant. Well, not really. Actually, it's going to look like a Gaussian. I mean, it's going to be flat indeed, because everything is flat. But when you look closer, if you will zoom, you will see a Gaussian. You know what the Gaussian does is like coffee milk, right? Or put sugar. So you take coffee, you put sugar on it, you mix, and then you get sweet coffee. Or you take a cup of coffee, you put milk on it. In the beginning, the two phases are separated. You see black and white. You mix. You let time evolve. You get this, mixed coffee milk, which is brown. And this process is highly irreversible. Once you mix, you cannot unmix just turning the spoon, all the way around. So what the Gaussian does, it says, okay, listen, so here I have a plot where there are positive aspects and there are some negative as well, right? But then the heat equation is mixing. The heat equation is mixing, right? And is compensating the positive and the negative. So the negative components have a mass, an integral, which is n minus. The positive components have a mass, which is m plus the positive integral. And then what the heat equation by mixing does, it produces asymptotically, the asymptotic behavior of U is simply n plus minus n minus times the Gaussian. Okay? So it takes the positive part and the negative part, it mixes. The mass that is left is the integral of the initial datum. Why the integral? Well, because the integral of the solutions, space integral of the solutions of the heat equation along time is preserved. And then the mass that is left, which is n plus minus n minus, takes the form of a Gaussian more and more and more. These oscillations have the tendency to disappear, right? These oscillations have the tendency to disappear, and they all adopt the shape of a Gaussian. So is this good or bad? Well, it depends. So for parabolic PDEs are fantastic because they have this regularizing, this simplification effect. Of course, this makes the process very highly reversible as well. I mean, you cannot undo the convolution. And this is well known in image processing. And because of that, you need to use Tikhonov regularization. And there are many, many things that are due to this irreversibility of the process. It's also dangerous in inverse problems because inverse problems, you are precisely trying to invert the forward map. A forward map that is extremely oversimplifying, it will be very, very hard to, you know, to try to solve back, because basically what we are saying here is that very many initial data that are different in nature, right? Different in nature, they lead essentially to the same Gaussian. Because basically what we are saying is that asymptotically, we are taking basically initial data which are, say, in L1 of the real line, which is certainly a very infinite dimensional Euclidean space, and basically the only thing we see here is the mass. So somehow the heat equation is a oversimplification process in which the initial data are taken and asymptotically they have led to one single value m. Of course, if I will think in terms of probabilities as we were doing for the neural networks, I will say, well, it's not true that if it's only the capital N, because if I fix the time very high, but not infinity, say n equal 1000, sorry, t equal 1000 but finite, I will see the Gaussian, but I will see also some rugosity, some oscillations that are left, and this keeps some memory of the initial datum. Well, yes, there are some details, but actually when you draw the picture, you basically only see m times the Gaussian. Actually, this phenomena is so fundamental, is so strong that I invite you to just check with MATLAB or any other tool, take the heat equation, put an initial datum at random, and let it evolve. You will see how rapidly you see the Gaussian emerging. So what is the analogy of this with all this burden of machine learning? Well, you see, when we are approximating PDEs by finite differences, this is what we do. We take time steps, right? We take time steps. So by replacing the heat equation by a time discrete heat equation, delta t, something like this. Okay, so you can make it time discrete, and then because I made it implicit here, it will converge without unconditionally, without a Courant-Friedrich-Levy condition. Oh, and I can also do finite differences in space, right?
This is a plus instead of minus. Huh?
Right. Thanks. Yeah, you need it to be, the operator to be negative on the right-hand side to make it well post. Good. So you see, now the way I see neural networks is the following. So how do you transform this very classical way of thinking of numerics of PDEs, in which time is evolving, right? So time is evolving. We feed here an initial datum that is very complex. And here, eventually, when time is very long, here we see something that is very simple, just m times g. So we have built a machine here, the discrete finite difference heat equation, by adopting this implicit finite difference scheme, which is well posed, is building a machine that has this very capacity of wherever the initial datum you feed here, it can be any value at every node, representing a very oscillatory pattern, possibly. It leads asymptotically something very simple, which is always this kind of Gaussian distribution, in which the only free parameter that is left is just the mass, is a scalar. So you move from infinite dimensional vectors, right? So this will be a vector in, say, a small L1 of Z, into just a number, So what is the analogy with neural networks? Well, neural networks, you have to think, this picture that we are used to draw this way in PDEs, X is horizontal and then T is vertical, very much conditioned by our understanding of the world. We are three-dimensional human livings, that we understand the three space dimensions of the space we are living on. And then for us, T is a fourth variable along which a space evolves. And this is how we represent it typically in PDEs, horizontal X, vertical T. In machine learning, you turn the axis around. And then all these entry nodes where you are feeding the information to the heat equation now are put vertically. And this is the first layer. And then each of the next layers that in the time resolution of the heat equation come in a time-like discrete manner, then become the next layers, right? So the third layer in yellow will be something like this, and so on. So this is the width, the height is the width, and this is the depth, and this is one layer, and this is the iteration layer by layer. And then there are many terminologies, many different architectures, depending on the connections you consider. People will call recurrent neural networks, multi-layer perceptrons, plenty of terminology to refer to the different possible architectures. So now, if you ask, you see the difference in machine learning with respect to classical PDEs is the following. In classical PDEs, we say, listen, there is mechanics. In mechanics, we observe diffusion processes, population dynamics, opinion formation, biology, infectious diseases, heat, conduction. Then we have the heat equation, the prototypical example. The theory says the heat equation can be solved using Gaussian heat kernels. You can push this theory very, very far to solve nonlinear, parabolic, PDEs, analyze regularity, free boundaries, and so on. And this is the goal of mathematical analysis. And then you can also develop numerical algorithms that are able to capture the fine properties of this PDE solution. So here, in machine learning, you are not doing this. In machine learning, you are free to invent the PDE you like, except that you don't invent PDEs. What you invent is discretized PDEs somehow. So you really invent how this neural network to the right will be constructed, and how you will choose the different coefficients here, right? So that so that the PDE does what you want. And what is what you want? Well, you want a PDE that is able to learn, meaning that you want a PDE that whenever you give me here the digits of a 2, which are plenty of zeros and then some ones on, you know, the location of the graph of the 2, when you give me a 2, then the output at infinity is a 2. And whenever you give me a 7, then the output here is a 7. Of course, you cannot expect it to be sharp with a finite number of layers. The same as for the heat equation. You cannot expect it to be sharp, but you expect at least the neural network you have built to have the representation capacity so that you can allocate to every vector representing to any digit the corresponding label, its nature, either 2 or 7, in a rather precise manner with a high success rate, which means that these probability vectors you get should be mainly approximately Dirac deltas, and the Dirac delta be sitting, of course, in the corresponding location. So it's not sufficient to be very self-confident and say that a 7 is a 1. This doesn't help. If the 7 is a 7 and you say it's a 1, it's not because you are a Dirac delta. This means rather that you are totally wrong. You are a Stormborn and you say it's a 1 while it was a 7. So you need also, you know, to be matching the labels. Okay? So this is the link between PDEs and machine learning. You have to think on the machine learning drawings just oriented in the opposite manner with respect to discrete PDEs. And the difference in PDE theory and in machine learning is that in PDEs, the PDEs are given by God, by mechanics. They are given Navier-Stokes in 3D. Then problem, understand the solvability of 3D Navier-Stokes. While here, we are free to invent the PDE we like. So we have made the sigmoid enter dramatically. The activation function has been used massively in the construction of the machine learning algorithm. We could have tried to avoid this. So you see, for instance, there is a result, there is a famous paper by, I think it's Pincus, soon after Sivenko, when he said, oh, how far I can go with the density result by Sivenko. And then he proved, listen, basically Sivenko's theorem about density. Oh, you don't see do you see my iPad now? Yeah, you still see the iPad, right?
Yeah.
So Pincus said, how far can I go with these ansatz? And he basically proved, well, actually, the fact that the sigmoid fulfills this is not very surprising. He said, actually, all functions sigma, except for polynomials, fulfill this property by Sivenko. Why do you think that polynomials are bad? Why do you think in this context the choice of a polynomial as basis function for this neural network construction, this multi-perceptron one-layer neural network, the multi-perceptron? Why do you think the polynomial is bad? So take a polynomial, I don't know, sigma x equal to x squared plus 2x plus 1. This is a nice parabola. Why this sigmoid is not a good idea for guaranteeing the universal approximation? It can change convexity. Well, a polynomial of degree 2 is always concave or convex, but I mean, yes, you could take a 3 a cubic polynomial and then have something more sophisticated. But why polynomials are bad? Any guess? Well, polynomials are bad because if sigma is a polynomial of, say, degree 3, you check this and you see, what is this? Well, sigma is a polynomial of degree 3. The only thing you are doing is here you are introducing coefficients, but this remains always a polynomial of degree 3. And now, if you combine n times n polynomials of degree 3 linearly, you get a polynomial of degree 3. So this gives the wrong impression that you are increasing the search space. When sigma is a polynomial of degree, say, p, the Sebenko ansatz always remains a polynomial of degree p, regardless how many neurons you place and how well you choose the weights. So it's a bad idea. You need precisely a sigmoid function which is not a polynomial, like the Gaussian, the sigmoid, the ReLU, so that you escape out of the class, right, in which the initial function was confined, and you enrich the space of search when n grows. This is the only chance you have to guarantee the universal approximation. And then you say, well, ReLU is almost a polynomial, is 0 and 1. Yes, oh, sorry, 0 and identity x. Yes, but it's not a polynomial and it's sufficient. And you see why it's sufficient. It's because in particular, in 1D, you see immediately you can build all kind of piecewise constant functions, piecewise linear functions. Okay? Very good. So when we adopt this perspective of neural networks as being discrete like PDEs, where layer by layer we expect the evolution of our features, our initial data, like in a time discrete Cauchy problem, to the corresponding label asymptotically after many layers, and hopefully, of course, after a finite number of layers with some high probability, we are necessarily thinking on nonlinear PDEs because the sigmoid is there, right? So if you were thinking on the heat-like equation behind a neural network, it will be more like, I mean, I'm just guessing. I never thought of this before, but it will be more something like, yeah, something like this, like maybe sorry, and this will be you. Maybe this will be like something like this. Okay. So for those that are experts on nonlinear parabolic equations, right? You identify here a number of features, right? Like coefficients in your parabolic PDE, nonlinearity sigma, definitely the nonlinear aspect is fundamental, and then some kind of heat evolution, right? But in this heat evolution, the U layer by layer is feeding, one layer is feeding the next in a time evolution manner. This will be a monster of this file. And now the question is, how do you model the coefficients so that you can, to every initial datum, allocate the corresponding target? And this is precisely what this model does. So we don't need to get into the field of PDEs to do that. This is something, you see my slides now? ODE here at the top.
That's okay, that's okay.
is sufficient to do this, right? So let me just show you an exercise, and tomorrow we can discuss this a bit further. Let me show you an exercise. So this is a very simple classification problem in which you have 3 blue data, 3 green data, and 3 red. We all understand colors. And we have 3 baskets, the basket of the blues, the basket of the green, and the basket of the red. And now I have to properly choose the coefficients W, A, and B on this neural differential equation, so to bring the blue to the blue area without undoing the good collocation of these 2 blue, these 3 green, and these 3 red. So the problem is very simple. I have oversimplified the problem because out of the 9 dots to be classified, 8 of them are already classified. Only 1 needs to be reclassified. So it's very simple. But it is still a simultaneous or ensemble control problem, because I really definitely don't want that to place the blue, this one, blue, badly collocated into the blue area, you bring blues in the green, greens in the blue, reds in the green, and so on. No, you have to preserve also the collocation of the others. So the question is an ensemble control problem. Each item has to go to its color, meaning that those that are well collocated remain in their color, and the others are allowed to move in order to be placed eventually in the corresponding color. Now the question is, can you do this? Can you solve the W, the A, and the B so that each point go to the corresponding location? Well, we have done, computational experiments, and when you do it computationally, you ask the computer, please solve this huge optimization problem of training the coefficients W, A, and B so that this occurs. This can be done. I have shown you that yesterday. The yellows go to the yellow, the purple to the purple, and the green to the green. Now the question is, can I understand it? And then the answer is yes, we can understand it, because analytically, we can make an induction proof showing that this neural ordinary differential equation has the very property of simultaneous or ensemble control, and I can do the proof in an inductive manner. And then, because the proof is inductive, because every data set will have a finite number of data, large or small, this will take me longer or less time in order to classify all the data, but I will be able to do it. Why? Because I can use piecewise constant controls to control the system, and here, in 4 steps, be able to bring every item to the corresponding location. Okay? So this is a prototypical example in which you see these ideas of control and dynamical system, where time evolves horizontally. Data are represented in a finite dimensional Euclidean space by just pixels. So in this case, it will be very simple because data are just, say, blue, red, or green, right? And then data evolve. The controls A, W, and B are chosen in a piecewise constant manner. And once I make the strategic choice of the coefficients W, A, and B properly, I let the system, this is now a dynamical system that evolves in time. And when I let it evolve, I see that every initial datum, which is one of the initial dots to be classified, spontaneously, in a simultaneous manner, gets to the corresponding location. So the fact that I was able to build a time discrete system, a neural network that is able to allocate every initial datum to the corresponding label, is what shows that my neural ODE has learned. My neural ODE with the well-chosen controls W, A, and B. These well-chosen controls are those that guarantee that my neural ODE has learned that in this exercise, there were 3 different balls or 3 different types of balls according to the colors that should be placed in different locations. Okay? Okay, so we can continue then tomorrow. Tomorrow, I think we can start also with the questions you might have. And I will explain better this connection between neural ODEs, control, and classification. But now you have all the ingredients to catch this very quickly, and we can move into other more elaborate topics.